All right, so get ready because today we're doing a deep dive on something that has really blown my mind lately, and that's telegraph transmission theory.
Okay.
And I know what you're thinking, telegraph, isn't that like ancient history? But trust me, it's way more relevant than you might think, especially in our digital world today.
Yeah, that's right.
You sent over some incredible excerpts from this 1928 paper by a guy named Harry Nyquist, along with some more recent research on something called MR sampling. Have you heard of that?
Yeah, absolutely fascinating stuff.
I mean, it seems like Nyquist basically laid the groundwork for everything we do online without even realizing it, you know?
It's amazing how relevant his work still is, almost a century later.
So, just to give our listeners some context, we're talking about a time when telegraphs were the absolute cutting edge of communication.
Right.
So, what was Nyquist trying to figure out back then? What was the big problem he was tackling?
Well, in the simplest terms, he was trying to figure out how to send those telegraph messages, those dots and dashes of Morse code, across really long distances without them getting all jumbled up along the way.
Oh, I
Like,
saw.
imagine a dot at one end of the wire becoming blurry and turning into a dash by the time it reaches the other end. That's the kind of problem he was dealing with,
Oh, that makes sense.
trying to keep those signals clear over long distances.
And that's where the concept of bandwidth comes in, right? I mean, that's one of Nyquist's big contributions, right? This
Yeah.
whole idea of bandwidth.
Bandwidth is key.
Yeah.
He discovered this fundamental relationship between how fast you want to send information and the range of frequencies you need to use.
Okay.
It's like a highway. The more lanes you have, the more cars can travel at higher speeds without crashing into each other.
Right, right.
So more bandwidth equals faster, clearer transmission, just like a wider highway means more cars can travel faster.
That's a great analogy. And that idea of bandwidth is still crucial today, isn't it?
Oh, absolutely.
For everything we do online.
Everything from our phones to the internet, we're talking gigabytes of data traveling through fiber optic cables every second.
Right.
All thanks to those fundamental principles that Nyquist laid out.
Wow.
But what's really mind-blowing is that Nyquist didn't just stop at dots and dashes. He realized that his findings could apply to ANY kind of information, not just simple telegraph signals.
Oh,
And that's where things get really interesting.
right. Because at first I was thinking, okay, dots and dashes, how do you go from that to like the complex information we send and receive today?
Right.
So how did he bridge that gap?
Well, he discovered that you can break down any signal, no matter how complex, into a bunch of simple sine waves. It's like taking apart a complicated sound and analyzing each individual tone that makes it up.
Oh,
So every signal has its own unique combination of sine waves, kind of like a fingerprint.
like a fingerprint, right?
Exactly. And by understanding how a transmission system affects each of those individual sine waves, he could then predict how it would handle any complex signal, even if it was made up of thousands or millions of these individual components.
Oh, wow.
He was basically laying the groundwork for how we understand and manipulate signals today, even in our digital world.
That's incredible. It's like he created a sort of Rosetta Stone for understanding any kind of signal, no matter how complex.
Exactly.
Okay, so we've got our signals broken down into their individual sine waves, thanks to Nyquist.
Right.
But then he also talked about something called shape factors, which I have to admit I had to read that section a few times.
Right. It's a bit more of a nuanced concept.
So what are shape factors all about?
Well, this is where Nyquist's genius really shines, I think. He realized that the shape of a signal, how it changes over time, is just as important as the information it carries.
Really?
Yeah,
So it's not just about the what, it's also about the how.
precisely.
Okay.
Use the analogy of a hammer. Its shape is what makes it perfect for hammering nails.
Okay.
Just a signal needs the right shape to be transmitted clearly.
So if a hammer is great for nails, but not so much for turning a screw, is that kind of like saying that a poorly shaped signal is going to get distorted and lose information along the way?
Exactly. You've got it.
Okay.
And what's even more impressive is that Nyquist didn't just identify this problem, he actually came up with a solution.
Oh, wow. So what was the solution?
He figured out a way to pre-shape the signal at the sending end, to counteract the distortions it would experience during transmission.
Whoa. That's really thinking ahead.
Right.
It's like he's pre-distorting the signal in a way that anticipates the distortion it will encounter, so they cancel each other out and the message arrives intact.
Exactly. It's like sending a self-correcting message through time and space.
That's incredible. And to think he was doing all of this decades before we had the digital tools and computing power we have today, it's mind-blowing.
It really is remarkable.
Okay, so we've talked about breaking down signals into sine waves and shaping those signals for optimal transmission.
Right. But now I want to jump forward to the present day because you sent over some research on something called MR sampling, which sounds like it takes these concepts to a whole new level.
It absolutely does.
So what exactly is MR sampling? Give us the crash course.
Okay, so MR sampling stands for multi-rate sampling, by the way. It basically builds upon those foundational ideas from Nyquist, but takes them into the realm of digital signal processing.
Okay.
It gives us incredibly powerful tools to analyze and manipulate those individual components of a signal, those sine waves we were talking about, in ways that Nyquist probably couldn't have even imagined.
So it's like we've gone from using a magnifying glass to examine those signals to having a superpowered microscope.
Exactly. And with that increased resolution, that deeper level of analysis, we can now do some remarkable things. Like, for example, we reconstruct signals perfectly from samples, even if those signals aren't perfectly band-limited. Hold on, I need to make sure I'm following you. Are you saying that we can now take a signal from the real world, which is inherently imperfect and messy, and recreate it perfectly in the digital domain?
You got it.
How is that even possible?
It's like having a super-powered puzzle solver that can figure out the missing pieces, even when there are gaps in the information.
That sounds like magic. What's the secret sauce? How does this puzzle solving actually work?
The key is something called non-uniform sampling. Remember how Nyquist talked about sampling at regular intervals?
Right, like taking a measurement of the signal at every tick of the clock.
Exactly.
Yeah.
Well, MR sampling says, hey, sometimes you don't need to sample at every tick. You can be a bit more strategic about it.
Wait, are we talking about breaking the rules of sampling now?
In a way, yes.
This is getting even more interesting.
It's pretty amazing stuff.
So instead of taking a measurement at every tick of the clock, we can just grab bits of information here and there, and somehow it still works.
Exactly. It's like instead of reading a book page by page, you randomly pick out sentences. But with the right techniques, you can still understand the whole story. And this randomness, well, it's actually a really powerful tool.
Okay, that makes sense, I guess, but when would you ever want to sample randomly like that? What are the advantages of doing things that way?
It's especially useful for things like image processing. Think about it. Images, especially things like medical scans or satellite photos, they have tons and tons of information packed into them.
Right, huge files.
Exactly. And with non-uniform sampling, instead of wasting energy on every single pixel, we can focus our efforts on the areas that matter most, things like edges, textures, or areas of rapid change.
So it's kind of like, what do they call it, using a finer paintbrush on the details and broader strokes on the less important parts of the image.
Exactly. That means we can potentially get much clearer images with fewer samples overall.
So faster processing times.
Faster processing, smaller file sizes, all thanks to this ability to sample strategically.
It sounds like we could apply this to all sorts of things.
Absolutely, and people are.
This is incredible.
But I think before we get too far ahead of ourselves, it would be good to go back and unpack some of those other key insights Nyquist had about signal transmission.
Oh, for sure. I'm always down to learn more from Nyquist.
There's still so much to learn from his work.
So what else did he figure out that's essential for understanding how we got from those clunky old telegraph systems to the elegant world of digital signals we have today?
Well, one thing that I think often gets overlooked is how Nyquist tackled the problem of interference. Back then, remember, they didn't have those perfectly clean, noise-free transmission lines like we often have today.
Right, those wires were basically just strung across the countryside on poles, right?
Yeah.
Exposed to the elements and everything.
Exactly.
So lots of potential for interference.
Tons of it. And Nyquist realized that this interference, this noise, it was a major, major obstacle.
Made sense?
He even had a name for it. He called it characteristic interference.
So this wasn't just about things like thunderstorms or faulty equipment.
No, it was deeper than that.
So you're saying that even with the most pristine telegraph line in the world, there was still some kind of inherent noise baked into the system itself.
Exactly. Even subtle imperfections in the telegraph current, like tiny fluctuations in voltage or timing, those could introduce errors into the signal.
Wow, that's wild. I never thought about it that way, but it makes sense. I mean, every system has its limits, right?
Precisely.
So how did Nyquist propose to deal with this inherent fuzziness in the system?
Well, he was a big proponent of better engineering, for one.
Okay, sure. Makes sense.
He stressed the importance of using higher quality materials for the lines,
Oh, okay.
carefully calibrating the equipment, and even exploring new techniques for balancing and filtering the signals to try and minimize that characteristic interference as much as possible.
So it was about refining every aspect of the system.
Exactly. From the physical components to the way the signals were generated and processed, he was advocating for a holistic approach to improving signal clarity.
So not just making a stronger signal, but also reducing the noise floor, right?
You got it. He was laying the groundwork for what we now call signal-to-noise ratio,
Oh, right.
a concept that's still absolutely fundamental in everything from audio engineering to digital photography and, of course, telecommunications.
That's fascinating. So he was wrestling with this fundamental challenge of separating the signal from the noise long before we had all the fancy digital tools we have today.
Exactly. He was a true pioneer in understanding that clear communication isn't just about the message itself, but also about the fidelity of the medium through which that message is transmitted.
That's a really good point.
And that insight, it was absolutely crucial for paving the way for the highly reliable, high-speed communication systems we rely on today.
It's amazing how much we take for granted, like we just assume that our phones are going to work, our internet connection is going to be stable, but there's a ton of really complex science and engineering that goes into making all that happen seamlessly.
Absolutely.
That's all built on the shoulders of giants like Nyquist, who were figuring out these fundamental principles almost a century ago.
It really is incredible. And speaking of Nyquist's ingenuity, there's another significant contribution of his that I think is worth exploring. His work on carrier wave telegraphy.
Now, when I hear carrier wave, I immediately think of radio. Am I on the right track? Was Nyquist involved in the early days of radio transmission too?
You're absolutely on the right track. And while his main focus was on telegraphy, the principles he was exploring had a huge impact on the development of radio.
Okay, that makes sense. So we're talking about a time when telegraphs were still using those direct current pulses to send those dots and dashes, right? How did carrier waves change things?
Well, imagine that instead of sending those simple pulses directly through the wire, you could sort of embed them onto a higher frequency wave, what we call a carrier wave. It's like instead of sending a little boat out on a choppy sea, you put that boat on a much larger ship that can handle the rough waters more easily.
Oh, I see. So it's about giving that signal a more robust way to travel.
Precisely.
So instead of just sending out a single tone, which could easily be distorted or weakened, you're now layering that information on top of a stronger signal, which is less susceptible to interference.
Exactly. You've got it. And this, my friend, is where things start to get really interesting. Because this idea, this carrier wave concept, it opened up a whole new world of possibilities for telegraph transmission.
Oh, I bet.
And Nyquist, being the brilliant mind that he was, he dove headfirst into this new world, exploring different ways to modulate those telegraph signals onto those carrier waves.
So he was trying to find the optimal way to, I don't know, package those signals for long-distance travel, like figuring out the best design for a message in a bottle so it can survive a transatlantic voyage.
I love that analogy. That's a great way to think about it.
Hmm.
And his research led him to analyze two main methods of carrier wave telegraphy: symmetrical and single sideband transmission.
Okay, and I'm guessing each approach had its own pros and cons.
You bet.
So tell me, what's so special about symmetrical carrier telegraphy? What makes it unique?
Picture this. You've got your carrier wave, right? That powerful signal we were talking about. In symmetrical transmission, you basically create two identical sidebands on either side of that carrier wave.
Sidebands. Okay, so it's like having two copies of the message flanking the carrier wave.
Exactly. Like bodyguards protecting a VIP.
I like it, but it sounds like it takes up more space, right?
You're absolutely right. Nyquist showed that this method, while incredibly robust and resistant to interference, wasn't the most efficient in terms of bandwidth. Remember, bandwidth is precious, just like that real estate on the information superhighway.
Right. Always got to be mindful of bandwidth.
Exactly.
Okay, so if symmetrical transmission is like having two bodyguards for every VIP, what's the alternative?
The alternative is single sideband transmission. And as the name suggests, it gets rid of one of those sidebands.
So half the bandwidth.
Exactly. It's a brilliant way to double the efficiency of your transmission.
Okay, but I have a feeling it's not as simple as just chopping off a sideband, right? There have to be some trade-offs.
Yeah. You're absolutely right. It's like trying to pack for a weekend trip using only a small backpack. Yeah. You have to be very strategic about what you bring and how you pack it.
Only the essentials. Okay, so what are the challenges with single sideband transmission?
Well, Nyquist identified three main challenges. First, you need what are called phase-correcting networks. Second, you have to eliminate something called the quadrature component. And finally, you've got to find a way to suppress the in-phase
Yeah,
component.
okay, that sounds pretty technical. I think you're going to have to break those down for me.
Of course. So let's start with those phase-correcting networks.
Okay.
To put it simply, think of it like making sure all the instruments in an orchestra are perfectly in tune with each other.
Okay, I like that analogy.
If the timing is even slightly off, if one instrument is even a fraction of a second ahead or behind, the whole thing falls apart.
It becomes a sonic mess.
Exactly.
Okay, so phase-correcting networks are all about keeping everything in sync.
Exactly. Now, the second challenge, eliminating the quadrature component, that's a bit more technical. But basically, it's about filtering out unwanted distortions in the signal.
So kind of like static on a radio.
You got it.
Okay, and then the third challenge, suppressing the in-phase component. What's that all about?
Well, this one is all about preventing the signal from getting delayed during transmission. We want to make sure it doesn't lag behind.
So we don't want our message to arrive late to the party.
Exactly. And what's remarkable is that Nyquist didn't just identify these problems. He actually came up with ingenious solutions for each of them.
So he was a problem solver at heart.
Absolutely. He was laying the foundation for advancements that would go on to shape the entire future of telecommunications.
This is fascinating stuff. I can't wait to hear about those solutions, but I guess we'll have to save that for next time because we're just about out of time for today. All right, so last time we left off with those three big challenges Nyquist faced with single sideband transmission, and you said he actually had solutions for them.
Oh, yeah, he did.
I'm dying to hear these. So let's start with that first challenge, those phase-correcting networks. What did he come up with?
Well, for that one, he got really deep into electrical engineering.
How? So I'm guessing I'm not going to understand this part.
No, it's actually pretty cool, even if you don't geek out on circuits like I do.
Yeah.
Basically, he came up with ways to use electrical components to tweak the timing of those signals, make sure everything stayed perfectly synchronized.
So it's like fine-tuning an orchestra, like you were saying before, but instead of instruments, it's electrical signal.
Exactly. He was basically inventing new tools to manipulate those signals with incredible precision.
That's amazing, especially for that time period.
It really is. And then for that second challenge, dealing with that pesky quadrature component, those unwanted distortions we talked about, he proposed this method called phase discrimination.
Oh, okay. Another technical term.
Yeah, sorry, it's hard to get away from those sometimes.
Yeah.
But the basic idea is actually pretty straightforward. It's like having a noise canceling system.
Oh, okay, I get it. Like those headphones that block out all the ambient noise.
Exactly. But in this case, instead of blocking out sound, it's blocking out specific distortions in the electrical signal. So the message comes through loud and clear.
That's really clever. So what about that third challenge, that in-phase component that makes the signal sluggish? How do you fix that?
Well, Nyquist realized that by cleverly choosing where he positioned the carrier frequency, he could actually counteract that sluggishness.
The carrier frequency being that powerful wave that's carrying the message, right?
Exactly. He found that by shifting that carrier frequency closer to the edge of the transmission band, he could give the signal a boost and prevent it from lagging behind.
It's like giving it a shot of adrenaline.
Exactly.
Okay, but even with all these clever solutions, you said earlier that single sideband transmission could still introduce some inherent distortion, right? Like trying to fit a square peg into a round hole.
You're absolutely right. There are some fundamental limitations you can't completely engineer away.
So what's the workaround?
Well, Nyquist, being the genius that he was, found an elegant solution, something called vestigial sideband transmission.
Okay, I'm not even going to try to pronounce that.
It's a mouthful, I know. But the idea is actually pretty straightforward. Instead of completely chopping off that second sideband like a normal single sideband transmission, you just shave off most of it, leaving a little vestige behind.
Oh, I see. So it's like compromising.
Exactly. And that little vestige, it acts like a correction mechanism, smoothing out the distortions.
That's brilliant.
It is, isn't it? And the best part is, it's incredibly efficient in terms of bandwidth. It's like finding the perfect balance between clarity and efficiency.
It's amazing to me how much Nyquist was able to accomplish with the technology available back then.
He was a true visionary, that's for sure. His work laid the foundation for so much of what we take for granted today.
Absolutely. And speaking of which, how does all of this tie back into that more recent research on MR sampling that we were talking about earlier? Because that's the stuff that really blew my mind, being able to perfectly reconstruct signals, even from incomplete data.
Right. Well, it turns out that MR sampling actually takes a lot of those foundational principles from Nyquist's work and applies them to digital signal processing in some really powerful ways.
So even though they were working almost a century apart, their work is deeply connected.
Absolutely. It's like Nyquist provided the building blocks, and MR sampling is taking those blocks and building incredible new structures with them.
That's a great analogy. So how does MR sampling actually work its magic? You mentioned something about functional subspaces last time, but honestly, I'm still a bit fuzzy on that part.
Right, that's getting into some pretty deep mathematical territory.
I was afraid you were going to say that.
But I think I can explain it in a way that makes sense, even without all the equations. Imagine a library.
Okay, I like where this is going.
And imagine that instead of just having sections for fiction and nonfiction, this library organizes its books based on all sorts of different characteristics, writing style, length, time period, you name it.
So it's super organized with all these subcategories within subcategories.
Exactly. And those subcategories, those are kind of like functional subspaces. But for signals, instead of grouping books, we're grouping signals based on their shared mathematical properties.
So it's like each signal has its own unique fingerprint, and we're sorting them into these different categories based on those fingerprints.
You got it. And here's the really cool part. Signals that belong to the same functional subspace, they share this special property. They can be perfectly reconstructed from their samples, even if we don't have all the samples.
Wait, so we're talking about bending the rules of sampling even further than we were before?
Exactly. MR sampling, when used within these specific functional subspaces, it's like finding a cheat code for signal processing.
A cheat code. I like the way you think.
Uh-huh. Well, it kind of is, right? We're basically saying, okay, we don't need to follow the traditional rules of sampling here. We can be a lot more efficient, a lot more strategic about how we gather information, and we can still end up with a perfect reconstruction of the original signal.
This is incredible. It's like we've gone from using a magnifying glass to a microscope, and now we've got this super-powered telescope that lets us see the entire universe of signals in a whole new light.
That's a fantastic way to put it. In this new perspective, it's opening up all sorts of exciting possibilities in fields like medical imaging, telecommunications, and countless others. We're constantly pushing the boundaries of what's possible.
This deep dive has been an amazing journey. From the earliest days of the telegraph to the cutting edge of signal processing, it's incredible to see how it's all connected.
It really is. And you know what's so cool about all of this?
What's that?
It's that at its core, it's all about this fundamental human desire to communicate, to share information, to connect with each other across distances. And from those early telegraph operators tapping out messages in Morse code to the engineers and scientists developing these incredibly sophisticated signal processing techniques, it's all driven by that same impulse to bridge the gaps between us, to overcome the barriers of time and space, and to share our stories with the world.
That's beautifully said. And I think that's the perfect note to end on. This has been an amazing conversation, and I can't wait to see what the future holds for the world of signal processing and information theory. Thanks for joining me on this deep dive.
It was my pleasure.